Hello, welcome to this week's Twitch stream. Actually noticing that the ratio between on and offline viewers have been kind of like shifted towards like people who are watching the videos offline. So maybe we need to think about like changing the time slot. Maybe the time slot is unfortunate for most of you, or I don't know. Maybe we need to change the topics. Um, Probably need to send out a survey or something like this to actually figure this out. Um, so anyway, but we still have quite a few offline viewers, but it's more fun if all of you are of many of you are online and show up in the chat and everything. It's kind of like part of what it's made to Twitch, so that's why I want to improve that. Um, so today, um, hi T-Tref, good morning. Um, so today we are talking about not what is in the notification of Twitch. I forgot to change that. So we're not working on a solar heating controller. No. And we are not working on the logging. Also no. But basically, logging is pretty good. We probably should do a few little like polishing things and actually put out a version 1.0 for everyone to use, because it's like getting into shape now. So today we unlike in the not changed announcement, we are working on a NIF driver for GPIO. So first, let me tell you about drivers. There's two ways to actually. There's three ways to talk. There's multiple ways, among other things. Um, I'm feeling like nobody expects the Spanish Inquisition of Monty Python. So there's many ways to actually talk to the outside world from Erlang, to hardware or to other drivers or other things. The main ones are there is ports, which are basically like if you on a Linux box, if you open port, then you spawn a whole process, and the Erlang VM spawns a operating system process, and basically connects to its standard in and standard out, and potentially depending on how you configure it, it's also to standard error, and and then um, and then does basically talks over these pipes to the port, and when the process crashes, that's the advantage of a port. Like the LMVM doesn't crash because it's in a different process. So you can actually have a flaky program run in the port, and when it crashes, then you link the port to the port owner process, because there's always a process owning a port. And then when the port crashes, like basically owning process crashes, and if you have this on a supervisor, you have basically something that restarts arbitrary processes repeatedly. And you can have like whole groups of those. So very useful ports. We can't have ports on GRiSP because on Artemis we don't have other operating system processes. We are basically, the whole GRiSP thing looks like one process. So everything is shared, all the memory is shared. What we have is threads. We have POSIX threads on GRiSP from Artemis, and the Erlang VM also uses those for asynchronous I/O and stuff like this. What we so far had were so-called port drivers. Port drivers are, like from the Erlang side, basically look like ports. So you almost can't distinguish them. You also do open port, but you have a special, you basically use the name of the port driver instead of the path to the program to start. And the port driver is kind of like either dynamically loaded, but it's running in the Erlang VM. So it's running in the same context. So in the port driver, if you crash this, we crash the whole VM. But that's a thing we always have under Artemis, that basically when we are out in C-land, then we need to be very careful, because there we always have the potential to crash our whole VM. Fortunately, we don't have to go out in C-land too much. And my favorite way of writing drivers, no matter how they are written, is to basically do as little as possible in C, parse everything so that C has an easy task, so you don't need to kind of like do complicated parsing of arguments in C or whatever. And then basically do all the work, all the like massaging of the arguments and sending over binaries or whatever, putting stuff together so it's easy for C to actually talk to it on the Erlang side. Because on the Erlang side, we cannot mess up our whole system. We can only mess up basically our Erlang process. And that gets restarted potentially, so nothing bad happens. The third one, the third of the many options to actually talk to the outside world is NIFs, native implemented functions. So NIFs is the newest of those. The other ones are older, and basically it gives you the possibility to, when you call an Erlang function, that actually a piece of C code is behind it, and that makes it at the same time more easy and more complicated than port drivers. With port drivers look like an operating system driver. You have a table of callbacks, and we can actually look at the existing GPIO port driver to show you. And a NIF doesn't have all this scaffolding, so you just call a function, and you need to deal with everything yourself. One advantage of NIFs is they're more efficient than port drivers, and that's why the OTP team recently kind of like rewrote the whole I/O system, the file I/O system and everything with NIFs to speed it up. Before they couldn't do it because NIFs were missing a few features which didn't allow to actually do asynchronous I/O and stuff like this. But they are now feature complete in this case. There's a few nice to have features, but basically you can do everything with NIFs now. So in GRiSP, we didn't have NIFs for historic reasons, because what is very much like traditionally NIFs were very much tied to dynamic loading. So when you wrote a NIF, this was a dynamically loaded library, and if you looked at the code that actually activated the NIFs, there was a lot of direct calls like dynamic loader do this, dynamic loader do that, dynamic loader give me the name of the function, and etc. etc. In Artems, we don't have which is the basis for GRiSP, we don't have a dynamic loader. We can't load anything dynamically. There's a kind of like fake dynamic loader, but it does not what you would expect, and it would not work with NIFs well. So because of the lack of the dynamic loader, we need to actually bake everything into the image. So we statically link NIF, and we would need statically linked NIFs. So we need to statically link everything we actually want to add at the C side. And NIFs didn't have the feature. So I had on my list like, to kind of like fix this and make a version, like kind of fake the dynamic loading or make some trick to actually allow statically linked NIFs. Fortunately, a few years ago, the OTP team needed the same thing. They wanted to have statically linked NIFs for a project, internal project I don't know much about, only that it was porting Erlang to a very similar operating system than Artems. And it didn't take off, but the nice thing is we got the statically linked NIFs now. So now we can actually use NIFs on GRiSP. And until like a few months ago, that was a theoretical possibility. To tell the whole story, so linked-in drivers can be loaded dynamically, but they can also be statically linked NIFs, statically linked into the Erlang VM. So there's a table of statically linked drivers which you can fill, and we actually, when we have a driver, you put it in a special directory, and we patch this table of statically linked drivers, so it actually the Erlang VM knows about this. So we use our makefile magic, or not makefile, we're not using makefile, our rebar magic to patch OTP source code and make the statically linked drivers work. So with static NIFs, we needed this like scaffolding, the tooling, that it actually works more or less seamless, so that you can actually just put a NIF file somewhere and it gets actually baked into an OTP. And that is there. Kilian completed that, and there was an old Twitch stream where Kilian actually showed the first steps with the statically linked NIFs. And now we want to take this technology and change our GPIO driver to NIF based, because a GPIO driver is very it should be fast, it should be switch on and off fast, and we actually want to rewrite it anyway, or we want to add features to it, because what we want for several applications is pulse width modulation. What is pulse width modulation? If you have very often, when you want to drive a motor, you only have a switch. You have kind of like a switch that you can like change polarity. So you can basically switch on the power or switch on the reverse power, and that's it. You can switch it on and off, but you cannot like kind of like switch it on 50%. I mean, in theory you could, but the problem is that all these schemes where you really throttle the power to 50%, you would need to burn the extra energy somewhere. So you would need a lot of cooling on your electric circuitry. And switching on and off is much better because you don't need to burn the extra energy. So the faster you switch, the less energy you need to burn. And that's the background, by the way, behind switching power supplies. So they actually regulate DC power by switching a higher DC power, which is not so DC, on and off very quickly. And then have a capacitor which equalizes it out, and then you basically the more on ratio you have, the more power it has, or the more voltage it produces, or current, or whatever. And you make a feedback loop doing this. This also works well for motors. So, for example, for the robot car that we recently kind of like showed off. Actually, I wanted to show you the video. Let me get you the video. Let me get the video first, and then I need to find it first. I should have actually prepared for showing the video. It was a tweet, you might have seen it in the past. So. That was my last stream. Can't be long. Oh yeah, there we are. I'm just using Twitter website here. One moment. Pause. And I need to show you my desktop. Okay, so we had a tutorial in Berlin alongside CodeBeam Lite, and what they did there, we have a new robotic car, which you can see in the video. Can I actually make this larger? Oh, it goes full screen. I don't want full screen because you can't see full screen. I don't know how I can increase the size of the video by a bit, but I think it's seeable. I can paste you the link to the tweet, and then you can watch it yourself. So we have a new robotic cart, and what they did in the tutorial is they basically started with an empty directory and basically got the motor controllers working, and they made a remote control for it, basically via Wi-Fi with a second GRiSP board, and they used the PMOD NAV, the accelerometer in the PMOD NAV. So if you tilt the board, the remote controller board, actually you can make the cart move forward and backward and whatever. And that's when I try it out. That's the video from the tweet of this. So you can see this, the guy with the pink shirt tilting the board. I hope you can see this. Tilting the board, and then now he hands over the remote control board to the other guy. And you can see that the cart kind of like turns in circles and whatever. So this was a fun tutorial. I'll paste you the link so you can actually see the video for yourself, and then you can do it as much full screen as you want. So that's our new card, which we plan to use even more on. Yeah, there you see it. You see the GRiSP board on top of it, and all the motor controllers, and it's a 4-wheel drive. So we had a 2-wheel drive before, which we showed on several conferences, but now we have a 4-wheel drive, so much improvement. So yeah, that was this. But if you want to drive a robot like this, then something is still, I still hear it. Ah, it stopped. No, it didn't. Kind of like, I seem to have the window open. 1 second. Oh, it just restarted. I need to stop the window. Oh yeah. There you see the second reason why we need pulse width modulation. So the thing is, if you want to control the speed or the torque of an electric motor, you can use pulse width modulation easily, because you then control the voltage basically and the current, and then you can have a feedback loop and actually make it work, make it turn on a constant rate if you have like some feedback from the motor, that you know where it actually is. The second use case for pulse width modulation is the heating control. So the thing is, you can see here it's getting autumn. Let me make it larger. Yeah. So it's getting autumn, and you see like here it was like still like much sunny, so the buffer temperature was 90 degree, and now kind of like, yeah, we have like these, yeah, the days are a bit sunny, but it's a bit me, so we only get up to 60 degree, which is still nice to have a shower. It's all fine. Yeah, you see these little bumps is us taking showers mainly. So you can actually see our behavior. But yeah, the dishwasher and other things connected to the hot water also make bumps, so you can't see actually exactly where we are showering. But the thing is that the problem is then when we are here basically on before and after we actually start feeding in, before the yellow line goes up, we have a too low temperature niveau. And we can actually boost this up. So the sun is basically not strong enough to make really hot water, but we can actually boost this by basically pumping it slower. So we reduce the pump power, and then the water flows slower, and then it has more time in the sun to actually heat up, and then you can produce a higher temperature level, because to actually heat up the buffer, we need more temperature than the buffer has itself. So then we can have more percentage of the day over this, and also insulating the buffer better, like the pipes are out of the buffer, because this slope is much too steep actually. But yes, that's non-related to GRiSP. That's other things we do. So we want pulse width modulation. We want other features in GPIO like debouncing. I don't tell you about debouncing because we're getting into much like details. There's also like better ways than pulse width modulation and other use cases for pulse width modulation. So you can get these. I don't have any in reach. You can get these little servo motors like RC servos, like used in model kits, where you actually can set an angle. It should actually position to it. It's a servo motor, so it actually wants a position from you. And the standard servos actually get controlled by, guess what? Pulse width modulation. You basically, depending on the pulse width, like the on phase of the pulse width modulation, it actually sets to an angle. And that's how you control it basically. So pulse width modulation means, what does it actually mean? It means that we switch on and off, and we change the ratio of on to off time. And that's our kind of like control thing. So, but today we probably won't make it through pulse width modulation. That would be a bit of a stretch. But today we want to start a new GPIO driver with NIFs. And at the same time show you how to actually wire up a NIF into your application or into the GRiSP application. So what we do is we make a new GRiSP app. I really prepared for this. I pre-typed this line. So we make an empty new app. So I hope the noise is not disturbing you too much. We make an empty app with rebar 3 new GRiSP app, GPIO NIF test, and if we want to actually include C code, we need to configure it a little bit differently than normally. So what we need to do is, let me get you the Emacs window in here. We need to actually look at this project Twitch, GPIO NIF test, rebar config. So normally we have like, that's the default boilerplate that rebar 3 new GRiSP web gives you. You have a GRiSP section. There's an OTP version defined. And then you have a deploy section where you basically put the path to your SD card. Let me just like edit this to make it work immediately. Volumes. So I usually format my SD card with the name GRiSP. And on a Mac, they get mounted to volumes GRiSP then. So that's, we can immediately overwrite an SD card and then try it out on this board. And if you want to actually build OTP yourself, because that's what you need. If you, anytime you want to, you need to add C code. And let me just grab this from here. Then you need another section, because that's another command basically. It's the build command, which builds OTP. And I just cut and paste this because I don't want to kind of like type in this long path. So you need to tell the rebar, align mode, so we get the colors nicer. We have a section called build, and we actually need to tell it where the toolchain is. And the toolchain basically gets a directory. And on my Mac, I install everything under opt GRiSP, and then the kind of like hash of the toolchain basically version, so I can have different versions. GRiSP software, Artems install, Artems, and the version at the moment from Artems is 5. So that's where actually it expects to find the cross compilation tools and all the libraries basically. So the rest, the rebar plugin knows how to deal with the rest. So that's that, and in order to so the thing is, what we want to do is, since this is the GPIO driver, so normally you would put the NIFs. So if this is your application, you could make so every part of every application in a GRiSP system can have a GRiSP subdirectory where you have certain subdirectories in the GRiSP subdirectories, and there's one for drivers and one for NIFs and all kinds of other things. You could basically, in every application, you can actually put these files. And what the rebar plugin does, it collects all the C code and bakes it into OTP. In our special case, where we actually want to improve the GPIO driver that is actually built in to GRiSP itself, we actually need to edit GRiSP. So normally you wouldn't do this, unless you would work on a base level driver that you actually plan to submit back to GRiSP, like something generally useful. Then you of course you can actually do a pull request to GRiSP, and we would look very much forward to it. So what we do here is now we go into this GPIO NIF test, and we make a directory called checkouts, and that's kind of like some rebar magic. So you can have a dependency. And GRiSP is always a dependency for GRiSP things. And I think, is it implicit or is it explicit? No, it has, you see the dependency GRiSP. It always depends on GRiSP. And the checkouts is some rebar magic that whatever you clone in there or symlink in there, basically is taken from there. It does not go to the internet or to Hex or whatever and downloads the dependency. So you can actually have multiple dependencies linked here or checked out here, and that's what we will do. We basically get a new window, let me get the path. So GitHub GRiSP, because I never can remember these path. So we basically want to clone the GRiSP application because that's what we want to change. So we go here and say clone or download, and we clone this SSH because I'm allowed to, because that's my repo. Git clone, and it has the keys, and we clone it into checkout. So from now on, it would not pull the dependency GRiSP, but it will take it from here. Okay. So let's try this out. So the thing is, if you don't change anything, it would still kind of like be able to use the downloadable OTP. So what we have is basically pre-built OTP, because the cross builds are basically independent of the operating system you're running. So we pre-build OTP and have all kinds of versions stored on a hash in some download area. And the Reaper plugin actually knows whenever the C code basically it kind of collects has a certain hash, confirms the hash, so there's kind of canonicalized and sorted and whatever, then it actually knows, oh, I can use this downloadable OTP. But in this case, we don't want this. And I'm not sure what happens if I don't change anything, but I have a toolchain defined. I'm not so sure. So I don't take any chances, and I actually, oops, sorry. Wrong Emacs. There is my Emacs, yeah. So we actually go in there and change a line or add a file. Actually, we should add a file. So we have checkouts GRiSP, and in GRiSP there's a GRiSP directory, and GRiSP space is basically the name of the board. And then we have drivers files, GRiSP conf, and there should be also a, let me check it out, a directory called NIFs. So basically, if you would make a directory here that's called NIFs, then it would actually use this. And I think we don't need to mess around a lot. We basically make a directory called NIFs here. So yes, we have this. And we just do this here. So we go to checkouts, GRiSP, GRiSP base, and we make a directory called NIFs, and we put something there. And I have a kind of like the thing that Kilian made in his Twitch stream. He kind of like got me this, which is a NIF that actually allows us to set the clock, and probably want to integrate it anyway. So we just put it here. Let me download this from here, because then I have a NIF where I'm sure that it works, because disclaimer here, because of my involvement with move home downloads GRiSP clock NIF period. Because of my involvement in embedded systems, and we didn't have NIF back then, my experience with NIF is very limited, basically none. I did not write any NIF myself. So this is like me learning writing NIFs also. So you can actually surf my shoulder while I learn writing NIFs. So we have a NIF here now. So we have GRiSP clock NIF. And let's have a look at it, or let's do it in Emacs. Nicer, because then we get syntax coloring. So we now have a NIFs directory, and that's the NIF. So what do we have here? Oh, that's interesting. How did that happen? Looks like a Unicode. Oh, that's Kilian's shell thing, then when he pasted it to me. So no, you basically remove this. And the way it actually starts is to actually make a statically linked NIF, you need to define static Erlang NIF. Otherwise it won't work. So it basically tells the Erlang compile system how to do this. And then basically there's a header from OTP that actually gives you a few predefined things. And then we need a few headers from Artems for this NIF. And then basically Kilian's first test NIF was a NIF that actually computes the square of an integer. So we can try this out. And yeah, and let's just build this. Because this will take a time, so we want to do it early. So now we basically changed our C code because we added something. And that would actually need to trigger. So let's test this. Rebar 3 compile. So compile is fine because it just compiles beam files. Nothing special here. But rebar 3. Do I actually tell something? Oh, I forgot my rebar 3 commands. New window. Let's look at the tutorial. Again, GRiSP GitHub. And we go to the GRiSP Erlang, and here in the wiki and on our GRiSP.org website, we have a tutorial and advanced tutorial, building the VM from source. That's where it's basically done. You can basically clone the toolchain. I already built the toolchain. We added the toolchain to our directory, so that's already done. And then the command is rebar GRiSP build. I didn't know if there was something special here. GRiSP build. And what that does, it actually... Oh, you're joking. Oh, I forgot to save probably, huh? Rebar config, and this file is not saved. And that's why we don't have a build thing. So you basically, if you don't tell rebar where your toolchain is, you can't build. Yeah, well, fair. So what it does is actually clones Erlang OTP. This may take a while. So it clones basically Erlang OTP from the normal sources. Normal? What? I'm not sure if we used to have our own fork, but I'm not sure we improved on that. So that's actually old. Let's shrink this. And that's also not necessary today. So yeah, so while this happens, we can read up on how to do NIFs. Because we are missing something, we need an Erlang file also for NIFs. New window. So there's a NIF tutorial on erlang.org. I'm not sure, do I need an Erlang file which actually has empty stubs or not? That's the question. So let's look at the NIF tutorial. So we need so even if all function module are NIFs, an Erlang module is still needed for two reasons. The NIF library must be explicitly loaded. We don't do this. All NIFs of a module must have an Erlang implementation as well. Oh, really? Minimum stub implementations. Loaded by calling Erlang node NIF, which you probably don't need to do. And basically the Erlang stubs. Oh yeah. So it's now it cloned everything, and now basically we are cross-building OTP with our included NIFs, with a patched makefile for building OTP. NIF library code. That's the library code. Running the example. You compile it. You run Erlang. You compile the. Yeah, I assume I'm not sure if you need the Erlang code. If you need the Erlang code, if we have a statically linked NIF, because unlike, no, it also has these NIF functions, and it has LNIF in it. Well, we try it out. So assumingly we need basically a file like this with I'm really asking myself why we don't have this put up somewhere. But I think we can figure out how to make this thing. So we probably don't need Erlang load NIF. That doesn't make sense. But maybe we do need it. I don't know. And the module here is complex 6. And basically that's the same module that you specify here with the NIF functions. And then you have complex 6 and foo and bar here. Okay. Yeah. So in the meantime, while we're building this, let's put the editor up again and have a look at our implementation. And then we can also look at the GPIO implementation. So this is in checkouts, GRiSP, GRiSP base, NIFs, GRiSP log NIF. So what we have here is basically the function square NIF, and basically they have a certain prototype. You get an environment, you get an argument count, and basically it looks very similar like a main function. You get an argument vector, and that's the arguments you get basically. And here we basically do is there's helper functions defined. So you can do NIF get int, basically give it the environment, give it the index of the argument, and basically give it an address of an int in this case, and then it basically puts the int there. And if it doesn't match, you get a make bad arg. And then we calculate our square, and then we have an NIF make int, which basically makes an int, again with the environment and the return value, and we return it. So that's basically how it works. So Kieran also worked on a set clock NIF. So because we have on the GRiSP one, we have one issue because there is no real-time clock. But even if there is a real-time clock, even if there's a real-time clock, it would draft. They are not precise, and you want to set it again later on, or you set it the first time. So you need some way to set clock. And the thing is that in Erlang there is nothing to set the clock of the operating system. I don't know any function there. If anybody knows a function, like put it in the chat or send it to me. But I think it's not there. So what we are using is, we are using basically rtimes timespec set, and then we use clock set time, which basically sets the real time. And that allows us, in another Twitch, I started it, and I think, I'm not sure if Adam did this on a Twitch stream or he improved on it. We already have, I think it's public, we started a simple NTP client in Erlang that gets the time from an NTP server, and the missing link was actually we want to set the time of the machinery. And that's what we do here. And there was some issue because of, like, you need to run it in certain time warp modes, otherwise it wouldn't work. So that's the testing. It's still compiling. You see, this takes a while. Compiling like all of OTP. So while we're doing this, actually let us have a look at the GPIO driver. So let's look from the top down maybe. So we look at the Erlang source first, and we have GRiSP GPIO and GRiSP GPIO drive, and then there's poller and printer and whatever. That's just helper functions, which probably shouldn't be necessary. So GRiSP GPIO it's a very simple file. It probably can be improved. So basically it's a gen server. Yeah, it is a gen server actually. So we run everything through a gen server, and we basically have get pin, clear pin, and set pin. So get sets it to 1. Get reads the pin value if it's an input. Clear basically sets it to 0, and set sets it to 1. Oh, we are done compiling. So actually this compiled, and we might be able to try it out. So we deploy it on the SD card. And it will probably crash horribly because we don't have the NIF. And now, embarrassingly, I lost my SD card adapter. Where did I put it? I always use it, and then I clean up the table for the stream, so you see a clean table here. Oops, oh sorry, that kind of like, so let me check the camera. Is the camera still working? This is embarrassing. Where did I put it? I have so many of these adapters, it's horrible. The motor we want for later, or probably for the next stream if I look at the clock, because I need to stop sharp today. Oh, this is really annoying. Sorry for that. Put it maybe on the back side. I have so many of these SD cards. Ah, there it is. Got it. It was buried under a little pile of old GRiSP boards. So we have, that's what, you're not seeing this. That was the thing I was looking for, like to put it in my computer. So we take the mini SD card, put it in there, and I put it in the computer, where it's supposed to be showing up in, let's check, volumes, GRiSP, yes. And one thing we need to add is we should clean the old stuff that's on there. And you probably have an example in rebar config foo. No, it's not. Simple control. I don't have it open, so let's just steal it somewhere else. Rebar config, because there's extra stuff we want in the deploy section. So rebar config in GPIO NIF test. So we have our deploy section only has the destination, but we want the prescript, which basically cleans the destination, so we get rid of the old garbage there. Oops. So we want this, and we want the postscript that ejects the card, because it's very convenient. So that's basically pre and post deployment. Don't forget the comma here. Okay, so we fixed the rebar config, and now we can do rebar 3 GRiSP. Oh, can you still see this? I think I moved my window. Yeah, now it's at the end. Maybe move it a little bit higher. Rebar 3 GRiSP deploy, and it wants -n, which, because you can have multiple releases in there, but our release is called GPIO NIF test, and the version is default version. When you do a new one, 0.1.0. So that actually should put everything on the. So here you see it tells us using custom OTP, and it tells us actually which hash it would have, at least as a shortcut. So we have a custom OTP because we changed OTP, so it doesn't use the downloaded one. So yeah, volume ejected. So this worked. So let's put it in our GRiSP board and boot it up. Power it. Wrong way around. So the usual thing to make, and we want the serial application to actually, it's already showing something. I had some error messages here. So yeah, this is already set up from last time. So we're booting this, and then we'll see, can we actually call this function without an Erlang file? Probably not. And next, basically, we then can kind of like, I assume this one is actually hooked up to the Wi-Fi. Oh no, it's not, because we have a new application and we didn't do this. So we should actually copy this. Let me do this quickly off screen, because you would see my Wi-Fi password. Because that's always annoying if you really want. So yeah, most of the things you can see. So in basically we steal this from the solar heating controller. In GRiSP-based files, you have a few config files. One is init.rc, so you can actually avoid having DNS running on the embedded system. So you can actually tell it, for example, the IP address of my computer. So that's not a big secret. So we actually write this into the respective directory of GPIO. 10 more minutes. GPIO. Nope, not check. Yeah, check. Is this into checkouts? No, this is actually going into GRiSP base files. So it doesn't exist. So Emacs asked me if I create the directory. So now we actually have this GRiSP base directory also. So that's basically the files we have, GRiSP base files. So you see here that this is a local thing. So while this is booting, we can actually improve the thing. So, but we can actually try to call our NIF directly, which probably wouldn't work. So this would then be GRiSP clock, and let's try the square NIF. Yep. So as expected, it wouldn't work because you need the respective Erlang file. So now we need to figure out where this kind of where would you put this? So this would also go into GRiSP. So this would be going into source. And we would need a module of the same name, GRiSP clock.earl. And we want to export functions square 1, and let's have a look at set clock. How many arguments does this take? Also 1 argument, or does it take 2 seconds and nanoseconds? So 2. And the other one is called set clock NIF. Really, it's called set clock NIF. Oh, the other one is called square NIF. So maybe just GRiSP clock square NIF. Just being adventurous here. Oops. No. Come on, my command line editing, this doesn't work here. But that's because we're still not square NIF. What? Ah, I use backspace again. GRiSP. I thought I had line editing mode and local echo on. This is annoying. Let me see. Terminal settings. Terminal settings. Echo type characters. Emulation. Send mode interactive. Line buffered. Okay. So because our TermOS is pretty broken, that's the one from Artems, and it doesn't have like nice line editing stuff. Actually, we would have another TermOS implementation for the console in the libbsd. That's also where the USB and the network drivers come from, and the network stack comes from FreeBSD. And there's also a TermOS implementation in there, but we are missing the scaffolding to actually replace the TermOS, the built-in TermOS, with something from a library, because this needs to be configurable, and that kind of like nobody worked on that yet. You probably should. But most of the time we are only using square NIF 5. We're using remote shell, and then you have nice. So it's still not defined, doesn't help. So we basically have square NIF 1, NIF 1, and we have set clock NIF with 2 arguments. So that's what we export, and then when you look at, I don't know if you need the init function because we don't load the NIF. Do we load it anyway? So that's kind of like from the tutorial, copied it from the tutorial. I don't know, I don't know, keep it in or whatever. It would be nice if Keelan would have written a tutorial. We definitely need a NIF tutorial. So this is, yeah, up on my agenda. And then we have square NIF, anything, library not loaded, and basically the other one is called set clock NIF. Set clock NIF, and it has 2 arguments, and we also do library not loaded. And we keep the load NIF. I don't know what to do, but it kind of like seems the prudent thing to do. So we need to build it again and put it on the SD card again, and then boot again. And then probably I'm done for the day because I really need to stop shop. Let's do a quick compile. Bad export declaration. What? Missing the square brackets. Nobody spotted this. You're not watching. Oh. So I should have done this before. So now it compiles. So we do deploy. So it recognizes that you didn't change the C code, so it uses the custom OTP. If it recognizes that we actually didn't change the C code, then it wouldn't. And yeah, volume is ejected, so we get our SD card, put it in the GRiSP board, push the reset button, and do the usual waiting. So while I'm doing this, I need to quickly send out something for my next call. Zoom. Okay. Starting Erlang runtime, we are waiting. And well, that would be a nice success at the end of the stream to actually be able to call the NIF. Of course, we didn't write any GPIO driver NIF because we are just getting started. But whoever picks up next, maybe if I pick up next, I don't know if we will have a gap of other topics. Then oh, come on, boot. So we then can actually pick this up again and have a much faster start. Thought it might be nice to actually explain how to actually get this started to work on NIFs. Because that's actually a nice thing to have in GRiSP, that you actually in a NIF you can talk directly to the hardware. So now we call, I really hope this works now because I don't have time anymore. GRiSP clock, no, don't. GRiSP clock square NIF 5. Ah, come on. NIF library not loaded. So maybe we need to call GRiSP clock init. I thought this would be called by itself, but I have no idea. I can't type. Sorry. Init. Oh, we didn't export it. Oh no. Init 0. No. Yeah, I'm sorry. I have to run. I cannot give you the success, but Kilian basically already did this. I suppose when everything is done correctly, it would work. Okay, so have a nice day. Thanks for watching. See you probably not for a while. Other people will be streaming because I'm on vacation starting next Friday. Okay, so see you after my vacation. But there will be basically watch the announcements. Basically other people from us will do streaming. Okay, bye.